Hello there. Let's look at a binomial distribution situation. So one of the first things that we're going to have to do is check to see that this satisfies our conditions for a binomial distribution, which means, do we have our bins? So the first one here, the B, that's for binomial. And in this situation, we do have it. So yes, we do have it because you're either left-handed or not. You're left-handed or right-handed. I guess there's two situations, but even if there are multiple ones, we're just interested in left-handed. So there's two outcomes there. Now, are we independent? And this one also is going to get a check mark because this is done randomly. So yes. We're pulling randomly, so just because we found a right-handed person doesn't mean we're necessarily going to get that person's twin next. Maybe we're rolling dice going through the phone book, something like that. The number of trials is also listed. We're pulling 100 people, so yes, 100 people are listed. So we know how many we have, and then the last one's always a little bit funny. We do have the same chance for success on each outcome. Getting a left-handed person doesn't become more and more likely as we continue on. This is similar to the idea of independent events, but it's a little bit different. Independent meaning that they don't influence each other, and the same chance is simply that this 1/9 is staying constant throughout the whole thing. Okay, so you probably won't have to do all of these checkpoints in future problems, but it's good to know that these are the things that you're looking for to even set up a binomial distribution. So, that said, the big question is going to be, is this normal? And really it's just, is it close enough to being normal? Because if we only do this, if we only pull one person, they're either left-handed or right-handed, and that's not enough to set it up. If we only pull two people, we're probably just going to get two right-handed people. So it's really, is this number large enough to get enough spread so that we get a normal-looking distribution, as opposed to something that's probably clumped near one side, that we want it to be spread out in like a bell shape. So for this, we got to look at the expected number of successes and the expected number of failures. And the expected successes, that's actually the same as the mean, which is n times p. So for this one, we are doing this 100 times, and we have a 1 in 9 chance of getting somebody who's left-handed. So that winds up being about 11.1 repeating, or 11 and 1/9. That is greater than 10, so that's okay. That part's large enough. Now, the expected failures, a couple different ways of doing this. So if we got 11 people on average who are left-handed, we're going to have 89 some that are right-handed. But maybe you want to set up that formula, expected failures. And you can get that by the number of times you do the trial, which in this case is 100 times the probability of failure, which is 1 minus the probability of success. And we get 88.8 repeating, I think. And that is also larger than 10. So this implies that it is large enough. The expected number of successes and failures is bigger than 10. So we should get some kind of normal-looking distribution, which is fabulous. And we have the mean here. That's our mean already. If we only did this a couple times, it would probably be skewed right. And the last thing we can do is there is a formula for figuring out the standard deviation. I'm going to jot down the mean there. Standard deviation, that is going to be the square root of the number of times you do something times the probability of success times 1 minus the probability of success, or also the probability of failure. So you can plug in that 100 and the 1/9 and the 8/9, and it's perfectly fine to get this as a decimal. Could also show off a little bit, so we know the 10's going to come to the outside, and the 9's going to come to the outside. Then we got square root of 8, and that's 2 root 2. So this will be 20 root 2 all over 9, I guess. But we'll just get it as a decimal. Oh, 3.1415. Actually, no, it's not pi. 3.1426. Okay, 3.14. Interesting. Now, as we get into the next day's topics, this mean here and this standard deviation there, that's actually going to be critical for us because we've established here that the distribution, the binomial distribution, is large enough to be considered normal. So that's good. And as long as it's normal, then with the mean and the standard deviation, we can set up z-score tests and get percentages. All right, thanks for watching Character and Scholarship for Life.